Hello, I am the instructor, Wang Shengda. In this lesson, we will learn about intermolecular forces. Through this lesson, you will understand intermolecular forces and their types. You will master the concept of cohesive energy density. You will be able to accurately state the types of intermolecular forces and their relationships and differences. You will be able to determine the material's applications based on cohesive energy density. The structure of polymer chains, including short-range and long-range structures, determines the basic properties of the polymer. The aggregated structure formed during polymer processing directly determines the final properties of the polymer. Different processing conditions result in different aggregated structures of polymer materials. This leads to different properties. Studying the polymer aggregated structure, its formation conditions, and the relationship with material properties is crucial for selecting and controlling processing and molding conditions. It also provides a scientific basis for polymer synthesis and modification. The polymer aggregated structure is essentially formed by the interactions between many polymers. The presence of intermolecular interactions causes the same or different polymer chains to aggregate together. Therefore, before discussing the polymer aggregated structure, it is necessary to understand intermolecular forces. There are mainly two types of intermolecular forces. The first is van der Waals forces. These exist between all molecules. We know that like poles of magnets repel each other while opposite poles attract. Molecules can also be viewed as magnets. Take hydrogen chloride molecules as an example. The hydrogen atom carries more positive charge, while the chlorine atom carries more negative charge. Thus, the aggregation of two hydrogen chloride molecules is the result of the hydrogen of one hydrogen chloride molecule attracting the chlorine of another hydrogen chloride molecule. This continues similarly. The second type of intermolecular force is hydrogen bonding. It refers to the intermolecular force formed when hydrogen atoms on an XH bond, where X is nitrogen, oxygen, or a halogen, interact with the Y atom on another bond to form hydrogen bonds. Take water molecules in ice as an example. Water molecules can also be viewed as magnets. The hydrogen atom carries more positive charge, while the oxygen atom carries more negative charge. The hydrogen and oxygen atoms between different water molecules form hydrogen bonds. Some polymers also have hydrogen bonds. The most common example is polyamide. As shown in the diagram, there is a hydrogen bond between the oxygen atom on one nylon chain and the hydrogen atom directly bonded to the nitrogen atom on another nylon chain. Consider this question: how does ice turn into water? The simplest way is by heating. How does water turn into steam? Again, by heating. So, in the transition between solid, liquid, and gaseous states of water, or in the transition between the states of all molecular substances, is there a chemical reaction involved in the conversion between these states? The answer is no. The conversion between these three states is essentially a process of overcoming intermolecular forces. Compared to small molecules, the polymer aggregate structure has a significant characteristic. There is no gaseous state. The reason is that polymers have very high molecular weights, and the polymer chains are long. This leads to intermolecular forces, also known as bond energy, between polymer chains that exceed the bond energy of a single chemical bond. This means that when a polymer transitions from liquid to gas, chemical bond breakage occurs before overcoming almost all intermolecular forces. Bond breakage means the substance is no longer the original material. Therefore, polymers only have solid and liquid states, but no gaseous state. For polymers like polyacrylonitrile, The intermolecular forces between molecules are so strong that the corresponding material exists only in the solid state, not even in the liquid state. Intermolecular forces significantly impact many properties of substances, such as boiling point, melting point, solubility, viscosity, and strength. The magnitude of intermolecular forces in polymers is expressed by cohesive energy or cohesive energy density. Cohesive energy refers to the energy required to remove all intermolecular forces from 1 mole of a substance. Cohesive energy density refers to the cohesive energy per unit volume. This is denoted by CED. In general, if the cohesive energy density is less than 290 joules per cubic centimeter, it means that the polymer has relatively weak intermolecular forces. Rubber satisfies this cohesive energy density. If the cohesive energy density is greater than 420 joules per cubic centimeter, it means that the polymer has relatively strong intermolecular forces. Fibers satisfy this cohesive energy density. If the cohesive energy density is between 290 and 420 joules per cubic centimeter, it means the polymer's intermolecular forces lie between those of rubber and fiber. Plastics satisfy this cohesive energy density. Therefore, the use of a polymer can be roughly determined by its cohesive energy density. It is worth noting that polyethylene has a cohesive energy density of less than 290 joules per cubic centimeter. But polyethylene is a plastic, not rubber. This means that cohesive energy density alone cannot determine the use of polymer materials. It must also be analyzed alongside the polymer's structure. In this lesson, we mainly studied intermolecular forces, their types, and the concept of cohesive energy density.